Hi everyone, if you just love antennas as much as I do, this video and the next one, DCL-431, are going to be very interesting to you. In this video, I want to talk about the voltages and currents in the antenna, and then in the next video, I'll talk about how those voltage and current variations create radiation that we call radio waves. I'm going to work very hard to keep this on an understandable level. We don't want to go too far with the math and the physics, but we want to go far enough to remain reasonably accurate. Now, at the end, I'm going to give you references if you want a much deeper understanding of this topic. And you can go pretty deep. This involves Maxwell's equations and quantum theory. Now, if it's that deep, do we have any hope of understanding antennas? I think we do. Did you know that to derive Ohm's law properly requires quantum mechanics? Now, most of us in electronics have a pretty good grasp of Ohm's law. We've never studied quantum mechanics. If we can do it with Ohm's law without quantum mechanics, I'll bet we can do a reasonably good job with antennas and antenna theory without quantum mechanics. The first thing we've got to do is talk about the dipole antenna. Now, this is a dipole I've used in the past. I've got it fed with open wire line, or what we call twin lead. The antenna itself is two pieces of wire separated in the middle, or they might be two pieces of aluminum tubing. Now, you can have a continuous dipole, that is, all one conductor. Here is a small Yagi antenna, and that little black thing is the gamma matching circuit that you connect your coax to. So the dipole doesn't have to be split in the middle, but in my example, it will be. Now, the first thing we want to talk about is the dipole antenna and DC flow in a closed circuit. Here we have a battery hooked to our antenna. Now, I know nobody hooks a battery to an antenna and expects something magic to happen. I'm just going to illustrate a point. So in this case, half the antenna is positive with respect to the other half. No current flows because this is called an open circuit. There's no path for electricity. If we put a short across it, we now have a closed circuit and we have plenty of current. How fast is the electricity flowing in the wires? Well, science tells us it travels at the speed of light, which is, as you can see, really, really fast. So if electricity is traveling that fast, and electricity is the flow of electrons, how fast are electrons moving in the wires? This is where it starts to get a little bit weird, in that the electrons can travel anywhere from a few centimeters per second to 200 million meters per second. That's all dependent upon the formulas we would use to determine how much current is flowing past a certain point, how big is the wire, things like that. So you see, electricity is made of current flow, but electricity and current flow aren't exactly the same thing. If you find that confusing, stick with me because I think I have a way of explaining it. You see, in the normal world of batteries and AC power, we can assume that electricity and electron flow are the same thing. We can assume that current can only flow in a closed circuit. In radio, we have to be more sophisticated. But don't worry, it's not that complicated. What we've got to talk about now is something I like to call marble propagation theory. I used to think I invented this, but apparently I read about this about 30 years ago and then forgot I read it and then thought that I invented it, but I'm sure I did not. I'm going to hold a hose up. You hold the other end at the exact same height. I'm going to start filling it with marbles that exactly fit inside the hose. Soon, the hose is full of marbles. If I shove one marble in, what happens at your end? Well, obviously, a marble will fall out on the floor. If there are 96 marbles between us, I shove a marble in at 1 marble diameter per second. Does it take 96 seconds for the marble to fall out of your end? No, because each marble pushes the next marble, and the marble falls out at your end at the same time I'm pushing my marble in. So the propagation of marble movement is way faster than the marbles themselves move. It's the same thing with electricity. Electricity is the propagation of electron flow, not the actual flow of the electron so much. Now, that propagation doesn't really happen at light speed in a wire, and many of you already know that. It's a little slower. For the rest of this video, we're going to pretend it is at exactly light speed to make the math easier. If you want to read about and learn about the variable speeds of current flow, you can watch any of these 3 videos I've got over here on the right. Actually, you probably want to watch all 3 of them. In any event, the propagation of electron flow is also called charge propagation. That becomes really important in the next video, but anyway, I'll walk you through it. Let's talk about current flow in open and closed circuits. We've already established current can't flow in a closed circuit, except, yes, it can. In the radio world, we do it all the time. All right, here's our open circuit. We put a jumper in. Now we have a closed circuit. Current is equal all around the circuit. Now, the voltage isn't quite equal. It varies as it goes through the resistances. So let's make the voltage variation more obvious. Let's put a light bulb in the circuit. The light bulb has a lot of resistance. The wires have almost none. As the current flows through the resistances, it loses voltage. So by the time we get out to the light bulb, we've only got about 11.9 volts. We lose a little bit in the wire, a little bit of voltage, not current. The current stays the same. Coming back toward the battery, we're going to lose another 1/10 of a volt. So you see we end up with 11.8 volts on the lamp, and we lose 2/10 of a volt in the resistance of the wires. So the voltages vary widely around the circuit, as you can see, but the current is the same everywhere. Now again, nobody hooks batteries to dipole antennas. So let's talk about charge propagation, and let's cross into the world of alternating current, not the direct current from a battery. Alternating current, if it's high enough in frequency, we call it RF current. This is a current that, now notice down here at the generator, which is my transmitter, we have this terminal is positive, this one is negative, we have current flow. When the polarity reverses, because remember, alternating current goes back and forth and back and forth and back and forth, everything changes. Notice also, I've got graphs up here. Let's go over here. At this point right here, we have a positive voltage that gets very high at the end. We also have a positive current that is very high, but it drops to 0 at the end. The opposite over here, negative voltage that gets very high at the end, negative current that is high, but drops off to nothing. This is part of the magic of radio and RF, and that is we can make current flow in an open circuit, and our voltages and currents are, I wouldn't say unpredictable, but they don't look anything like the DC battery circuit. Let's try to get an idea why all this is happening. Here's our humble dipole antenna. Now I've taken the feed line, the transmitter, all that out. We're going to pretend they're invisible, and the transmitter is right at those little blue terminals. What is about to happen? And what you see here is a graph of a sine wave at alternating current. Notice on the left side, the current and voltage are going to start going negative. But over here on the right, they're going to start going positive. So we have opposite charges being applied to this antenna. Before we get started, though, we'll do some very simple math. Each cycle takes very little time. because we're going to do 30 million cycles per second, which is 30 million hertz, or 30 megahertz. Now, these charges move down the wire at light speed. Let's make the math a little easier. Let's just say they move at 300 million meters per second, because they almost do. Now, if I have 30 million cycles of the AC wave per second, my AC wave takes 1/30 millionth of a second to happen. 1/30 millionth times 300 million is 10. So in the time this cycle happens, the current has flowed 10 meters down the wire. This is where we get the idea that a 30 megahertz signal has a wavelength of 10 meters. So one more time, the current moves 10 meters down the wire from the beginning of one cycle to the end of that cycle. That's fundamental to what we're going to talk about for the next 5 minutes. All right, so as I established before, both sides are going in opposite directions or opposite polarity. In other words, they're receiving opposite charges. So let's start the clock. We just get it started. And in the left side, we've applied a negative voltage or a negative current. So an excess of electrons is being pushed down the wire. Over here, we are applying positive potential. So electrons start to flow out. Now over here, this, I'm going to call it a clump of electrons, is going to start propagating down the wire because we've given it energy. The energy has to go somewhere, so the charge moves. Over here, as I pull electrons out, the electrons next to them start to move over, and then the next ones start to move over, and the next ones start to move over. So the positive charge, that is the lack of electrons, is moving this way. After we make it a quarter of the way through the cycle, and again, remember how fast everything is moving. A quarter of the way into the cycle, the charges have moved 2.5 meters, that's because that's 1/4 of 10. Now, a couple things happen. The charges have nowhere to go, so they're going to want to bounce back. But remember, in both wires, in the one on the left, there's a high negative voltage. Over here, there's a high positive voltage. Those voltages want to fight the charge from coming back. But look what's happening. Those voltages are decreasing. The charges are coming back. By the time the charges make it back to their origin, the voltage in both wires, being applied to both wires, I should say, is 0. So the charge can come back. But look, we're halfway through the cycle. Now our charge has moved, well, both charges have moved 5 meters, which of course is half of 10. Now, remember, you can think of these charges as moving. So think of it as if they passed each other as time keeps going. They've traded places, and at 3/4 of a cycle, they are now at opposite ends from where they were before, at a quarter cycle. They've now moved 7.5 meters because that's 75% or 3/4 of 10 meters. Of course, they're going to bounce back. And when they get back, they've now moved 10 meters during that cycle. Now you see why a half-wave dipole, 5 meters long, is the perfect antenna for a 10-meter radio signal. In case you didn't quite get that, at the beginning of the cycle, we have no charge. 1/8 of the way into the cycle, the charges are moving out. Quarter wave, or quarter of the cycle, they're out a quarter wave away. 3/8, they're back. At half, they've joined in the middle. Technically, they don't exist anymore. But now, polarities reverse. They effectively trade places. At 3/4, they're back where they were at 1/4, although on opposite ends of the antenna. 7/8 of the wave, they're through. Halfway back to their little trip back to the feed point. At the end, they're back. One more time, the quarter wavelength dipole is a fundamental building block of antenna design. Now, I've talked about the flow, that is the movement or the propagation of charges. We say that electrons, because they're negatively charged, have a negative charge. The positive charge is where there are less electrons. This is somewhat counterintuitive, but you kind of have to trust it. In DCL-431, I'll show you how the propagation of these charges make the radiation that we're trying to make in the first place, that is radio waves. We're going to pick up right where we left off. Now, as I said before, no one can teach all of this theory in two 25-minute videos. And no one is going to learn it all by watching just my or one other person's videos. I hope this has helped you get to a level of understanding you're comfortable with. Don't forget the next video, where, like I said, I'll pick up where I left off and we'll talk about how the charge propagation makes radiation. I know I've thrown a lot at you in this video. The yellow references are related content on my page. The white references are just some really good resources. WHJI.com is just great for all things radio. Tom is a tremendous RF engineer. These next two books, go on eBay if you don't have them and buy them. They don't have to be the 2025 editions. Just get an edition within the last 20 or 30 years. The Bill Orr book is also really good. The best book on antennas I've ever read is Any of the Three Reflections. He wrote this book 3 times. Now, if you're into calculus and physics and a lot of higher mathematics, Walter Lewin's series is really good, as are John Krause's books. But unless you've got some pretty good background in calculus, these books tend to be a little hard to read. Antennas is not too bad, but Walter's videos and electromagnetics are rather intense. In any event, I hope this was worth 18 minutes of your time, and I will try to get DCL-431 recorded and uploaded by Thanksgiving 2025. Thanks again for watching.